Okay, so welcome back to another video. So in today's video we have the infinite sum of 1 divided by 3n plus 1 times phi to the power 3n plus 1, where indeed phi is known as the golden ratio. So this is the first time utilizing the constant phi in an infinite series. I've actually used this constant several times in past videos, but they're mainly integrals rather. So this is the first for the channel. And so to tackle this, we're not really gonna start solving it by using the given. Instead, we're gonna take a look at it at a different perspective. Basically look at it at the same problem here, but with a different value. So we're actually not gonna include the 3n plus 1, but rather we're looking at phi to the power 3n. Use that to see like how we can rewrite and simplify some stuff out. So the answer I got, it's well, it does have a closed form technically, yes, but it's as simple as it gets, honestly, because simplifying out will just make things a lot messier, especially now we're dealing with the golden ratio constant, so there's a lot going on over there. You'll see eventually like what I'm saying. So I don't have any other remarks. Eventually we're going to convert this to an integral, so that also gives some surprise to the video as well. But other than that, let's actually just jump right in. So let's actually focus on looking at the infinite sum, specifically the same sum over here, but except as I mentioned, we're excluding the plus 1 to the exponent. So instead we're looking at 3n plus 1 times phi to the power 3n. But what you want to notice is that this is actually just equal to the series we're being asked to expand out. You'll notice that if you actually just verify this yourself, you'll see that that can actually be rewritten as the integral from 0 to 1 of phi to the power -3 times t to the t to the third power times n, or to the power n, then dt. So again, you can actually just integrate this and just to fact check, and you'll see that it actually comes out the same series that we're expanding over here. What we can do is by convergence, you can actually interchange the sum and the integral. So the integral will come first, and then we can write our infinite sum over here. So n is equal 0. Then now just write phi of -3, then to the power -3 times t to the power to the third power to the power n, and then dt. Then what you'll notice from over here is that this is actually in a form of a geometric series. So we see that since this is being integrated between from 0 to 1, so we can actually use that. So since the absolute value of t is actually strictly less than 1, then I'll just put geo, so for geometric series, we see that we can actually use the following. So over here we have that this is just the integral from 0 to 1 of our, well, convert this to an infinite sum, but it actually would be 1, then subtract, since the common ratio over here is just 1, but just 1, then subtract phi to the -3 times t to the third power dt. Now what we can do is let's actually do a little, before we continue further, let me actually write this a little easier. So we say that this is 0, 1 of 1 divided by 1 subtract. Since this is the power of the third, so what I can do is actually just factor out the exponent to the third power, and so we get that this is just instead t, and then divided by the golden ratio number phi, then to the power 3, and then dt. So from there you can actually perform a u substitution. So we'll let u equals t divided by phi, then take the differentiation both sides, so du is equal to 1 divided by phi dt. Then since we have to do the substitution for dt, I'll just factor out, or not factor, but multiply the phi to both sides, so we have that it's phi du is equal to dt. Then we can just move the phi, since it's just a constant outside the integral, so it's just phi. Then we have our new integral, so we have to evaluate this with our new bounds for u. So if I plug 1 for t, then this is just 1 divided by t. I'll write that as the exponent form, so phi to the power -1. Then plug 0, so that'll just be 0, so nothing's changed. Then we have 1, then divided by 1 minus u to the power u to the power 3 then du. So, and then what we established so far is that that's actually just equal to the exponent or the infinite sum that we were just analyzing. So n is equal 0, then 1 divided by 3n plus 1, then times phi to the power 3n. But since we're using it in that way, to that regard, so since we're given plus 1, so basically just multiply the phi, the constant phi, to both sides, or in this case divide since it's under the denominator, and you'll see that the phi will just cancel out. And so therefore we can see that the integral that we want to evaluate is specifically the problem that we are actually trying to evaluate. So we see that the infinite sum from n is equal 0 of 3n plus 1 then times phi to the power 3n plus 1 is simply just equal to just this integral, but delete the phi constant. So 0 to 1 of 1 divided by 1 minus u to the power 3 du. So it's smooth sailing from there, so we just have to calculate this integral over here. But it's actually not as easy as you think. You really can't do integration by parts, you can't do use substitution, so what do we do from here? Well, there's a little subject in Calculus 2, or Calculus 2 whenever you take it in college, as the partial fraction decomposition. So we're going to focus on our rational function 1 divided by 1 minus u cubed, then do the partial fraction decomposition from here. So what you'll notice is that if I fix this up a little bit, so this can be rewritten as 1 or negative 1 divided by u cubed, I'll write it that way, u cubed, then plus 1, then it has the following expansion as, let's see, let me first write the denominator here. That's the expansion of x, or in this case, u minus 1, then multiply with u squared plus u plus 1, and then negative 1 on the numerator. Or then it has the decomposition saying that if we try to find our numerators, so it's just in the form a, then divided by u minus 1, and add this with, since this is a quadratic, so the numerator is different, has the form of bu plus c, then divided by u squared plus u plus 1. Alright, so just do some cross multiplication to find our constants for a, b, and c. So we see that we have a square or ax square plus, or in this case u, not x. Sorry, my notes that I wrote it in terms of x, so I'm gonna get a little mixed up a bit. So this will be au squared plus au plus a. Then it's just doing the FOIL method from here, and we'll get that this is just plus bu squared minus bu plus cu, and subtract c equals negative 1. Now if we actually set these constants to each other from the left and right side, so we get the following systems of equation. So we set the u squared coefficient, so we would have that this is a plus b, and I set that equal to 0. For the u coefficient, this is just a minus b, then add this with c, also equals 0. And then for the constant itself, which is negative 1, well, from the right hand side specifically, we have that set that equal to a subtract c, and then equals negative 1. This is not that hard to show. What you can see is that I'll just add up these three equations together, and you'll see that we have the b's that cancel and the c's that cancel, so we actually found one of our constants. So we found that a is actually just equal to negative 1 divided by 3, and then if you just plug in the numbers back, so b is equal to 1 over 3, and then c is just equal to positive 2 over 3, like so. I just want to fix that over here. Let me write that as a slash. Now we just plug in back to our integrals over here. So here we have negative 1 over 3, then that's under x minus 1, then add this with 1 over 3x plus 2 over 3, then divided by, this is what I'm solving for u. See, I knew I'm going to mess this up whenever this is u, then u squared plus u plus 1. Then we can actually just do a little bit of factoring and simplifying as well, especially. And so we get that this is just negative 1 divided by 3 multiply with u minus 1, and then we add this with u plus 2, then divide this with 3 times u squared plus u plus 1. And so from there, we just have to integrate. So let's actually take things one step at a time. Yeah, and that's actually the simplest approach to go from here. So now let's integrate the first rational function. So -1. So here we have -1 over 3, then u minus 1 du. This is very simple. You guys, I'm sure all you guys taking calculus know how to do this. This is actually just -1 divided by 3 multiplied with the natural log. And for the sake of safetyness, since we're dealing positive numbers, let me just denote an absolute sign to this. And then this is just x minus 1. Or in this case, let's eventually later we're gonna have to evaluate the answer for, I'll rewrite this back as 1 minus x. It's still the same thing as natural log of x minus 1 since it's just positive numbers really. I know there's supposed to be a plus c since we're dealing with indefinite integrals, but since we have those bounds right over here, yeah, and speaking of which, this is supposed to be inverse phi. So phi, right, so eventually we have these bounds, we'll work with this later, so that's no big whoop, we'll get to it sooner or later. So we have this, so we have our first function integrated, so now we gotta integrate the second. So next, let's deal with, and that's supposed to be a u over here. I'm doing this again. I wonder if somebody keep a count of how many times I wrote x instead of u, please. All right, so next let's integrate this function over here. What I can do is I'll factor out 1 over 3 over here, and so we have u plus 2 then divided by u squared plus u plus 1 du. What we can do is we're going to rewrite our integrand a little bit different, so that way it's actually easier to integrate. So what I can do is I'll have a 1 over 3, and I'll split this up using linearity too. So, well, eventually once I get to that step, we have that this is just 2x plus 1, then divided by 2 times x, or u squared, u plus 1, then divided by 2 times u squared plus u plus 1 du. And then we add this, so add this with the 1 over 3, then the integral from, well, we're just dealing with the indefinite integral for now. So this will be 3, then divided by 2 times u squared plus u plus 1. So let's actually focus on dealing with this integral over here. So first, let's have, so the integral over here, let me just deal with this integral, I'll deal with the constant, I'll deal with this constant later. So 2u plus 1, then 2 times u squared plus u plus 1 du. Then I can just factor out the 1/2. So in this case, there's a 1/3, so I'll put that as 1 over 6. So let me just put the put this back as 1 over 3. Factor out the 1/2, so it'll be 1 over 6. Then the integral of 2x, or 2u plus 1, then divided by u squared plus u plus 1 du. I can just skip that work. You know that you just have to do a u substitution, set u equals u squared plus u plus 1, derive that, you get 2u plus 1, then you'll get in the form of 1 over, or the different variable 1 over x, for example, we'll just call it that way. But you'll see that this is just equal to 1 over 6, then times ln of, and I'll just deal with the absolute signs over here. So this is just x squared plus x, or in this case, u squared plus u plus 1, and then add a c, but again, we have our bounds, so we don't need to worry about that. Okay, so now the last part is we just need to integrate this function over here. So what I can do is, let's see, so if I factor out the 3 over 2, then the 3's will cancel, so we're just left with 1/2, then times the integral of 1 divided by u squared plus u plus 1 du. But what you'll notice is that you can't really factor out the denominator easily like that. So in other words, what we have to do is we can actually have to complete the square. And by doing so, this will yield us that this is just 1 then divided by, this will give us u plus 1/2 square, then add this with 3 over 4. So now let's actually do some substitution. Let's call this, hey, guess what? Now let's say x. X is equal to u plus 1/2, then dx is equal to just du, then just plug back the substitution. So now we have, yeah, so everything's good from here. So far it's just 1/2, then times the integral of 1, then in this case this will be x squared, then plus 3 over 4 dx. And what you'll notice is that this is actually forms a little, using the formula for the arctangent inverse trig formulas for integrals rather. So we have that, note that the integral of 1 divided by u squared plus a squared, for example, just use u, is actually just equal to 1 divided by a, then times arctan of u divided by a, and then plus c. We don't need to worry about the c since we have our bounds from over here. Now let's actually just put everything back together. So we have, so if I plug a, so a over here will have to be, this will be a is equal to the square root of 3, then divided by 2. Plug this back in, so this reciprocal flips, then the 2's will cancel, so I'm just left with 1 divided by the square root of 3, then times arctan of, so u, in this case u would be, or x rather, in this case x would have to be u plus 1/2, and then multiply with the a, which is, you flip the reciprocal, so we have that this is just 2 times u plus 1/2, but in other words, actually that's fine the way it is, I'll just distribute the 2 in, so this will just be 2u plus 1, then divided by the square root of 3. Excuse me, I almost had to burp. So we calculate this, we calculate these two are equal to each other. 1 over 6 ln of u squared plus u plus 1, that's equal to here. And then we just solve this integral. So now let's just take the sum of all those 3 we solved. All right, so now let's get into the grind. So now we have that the integral from the top, we say that that's equal to, so this is everything with commutativities of the addition, so I'll just move that around a bit. We have that this is just 1 over 6 natural log of u squared plus u plus 1, okay, then subtract with 1 over 3, then the natural log of 1 minus u, and then now add this with 1 over the square root of 3, then times arctan of 2u plus 1, then divided by square root of 3. And then we evaluate this with our bounds from 0 to inverse, the inverse of the golden ratio number. Basically, you just plug everything back in. As I said, there's not really a close form here. That's actually pretty hard to simplify from there, but I'm just going to write it out the way as it is. Well, to put this simply, what I can do is, and I'm just gonna skip that, you know, the writing portion of it, since it's gonna take forever to just put the space in and all that. But you can factor out, you could factor out the 1/2 from here. Then it'd be 1 over 3 times 1/2. Move that 1/2 to the inside of the natural logs using that rule, so it'll be the square root of u squared plus u plus 1, and then using your rules of natural logs, this is a subtraction, this is just the division of the same, well, not the same base, but like, because they share the same, okay, it's using your rules of natural logs, that's the other way to put it. So it's 1 over 3, then that shares 1 over 3, so in other words, I'll put it like this. So we have 1 over 3, then times the natural log of, so if I plug, I'm just going to plug the inverse phi, so this will be phi negative 2, then add this with phi negative 1, then plus 1, then divided by, over here this will be 1 minus inverse phi, that simplifies that out. Then we add this with 1 over the square root of 3 arctan of, oh, I hope I have it right, I should, 2 phi negative 1 plus 1, then divided by square root of 3, then move on to the next line, then subtract with, so you plug 0 over here, then plug 0 here. This is just arctan of 1 divided by square root of 3, then times 1 over square root of 3. That actually comes down to pi divided by 6 times the square root of 3, and the approximation shows that, and if I put this on Wolf out from over here, that it actually comes down to 0.6642, like so. Oof. And there we have it. Shoot, drop my marker. There we have it, the final answer in the black box. That's a lot going on, but dealing with golden numbers, this is actually pretty interesting. So yeah, that's pretty cool if you ask me.